Hi, my name is Jeff Squires. I work for Cisco Systems, and this screencast is entitled What is MPI? It provides a high-level overview of what MPI is and a brief introduction to the Open MPI project. So let's jump right in. What is MPI? MPI stands for the Message Passing Interface. It's what we call a de facto standard, meaning that it's not an official standard such as one by a standards body such as IEEE, IETF, or one of the various others out there. Now, it was written and ratified by a large group of people known as the MPI Forum, and this forum it was basically a body of academic research and industry representatives that capitalized on 10 to 20 years of parallel computing experience. So it did actually encompass a wide variety of views and go through a lot of debate before it was passed into a de facto standard, but it just didn't follow the same channels as the official standards bodies. Now, the MPI spec is actually two documents. There's MPI 1 and MPI 2, and these two documents specify interfaces in four different languages: C, C++, Fortran 77, and Fortran 90. Now, the MPI Forum published the MPI 1 spec in 1994, and then another spec, MPI 2, in 1996. And it's important to note that MPI 2 is really, for the most part, additions on top of MPI 1. So it didn't replace MPI 1. You have to take MPI 1 and MPI 2 in their entirety to understand the complete MPI specification. Now, the MPI Forum has recently reconvened at the beginning of this year, 2008, to start working on MPI 2.1, which is a number of little bugs that have been sitting around for a long time that really need to be taken care of. At the end of the MPI 2.1 process, we'll also issue a combined single document that encompasses all of MPI 1 and MPI 2. It'll make it a bit easier to parse and see the entire standard in its completeness. We're also working on MPI 2.2, which is slightly bigger bug fixes, which may entail some minor changes to user applications to be able to run under MPI 2.2. And then we're also working on MPI 3, which is just entirely new stuff that isn't included in MPI 1 or 2 at all at this point. So what is MPI? Well, actually, most people, when they say MPI, they're really talking about a software implementation of the specification. So it's usually host-side software, stuff that runs on a server and runs with some kind of application. We usually call this middleware because the MPI software sits between the application and the underlying network, whatever your network happens to be. And one of the big goals of the MPI middleware is that it simplifies network activity to the application. And what I mean by that is that we abstract away. Do you have shared memory? Do you have sockets? Do you have some other kind of network? MPI kind of hides all that from the application and presents a very simple interface to the application for moving bytes between processes. Now, a major point of the MPI spec is that you get source code portability, so that you can compile and run your application on, say, a commodity Linux cluster using one of a variety of MPI software implementations that are available there. But then you can also take that same application and recompile it on quote-unquote big iron machines where they have their own MPI implementation. They're not binary compatible, but at least you can recompile and relink your application and generally be good to go on a variety of different platforms. So here's a high-level view of what MPI looks like. At the top level, we have the user application. Then underneath that is the standardized MPI API. So there's functions like MPI send, MPI receive, and a variety of others. And then generally underneath that is some kind of operating system and maybe access to a network or what have you. But again, this just reinforces the point that I said in the previous slide, that MPI is middleware. It sits between the machine and the operating system and the user level application. So MPI is generally intended to deliver very high performance, and two metrics that people frequently cite, there are many more metrics, but two that people usually talk about are low latency and high bandwidth. So when I send a message from one process to another, it gets there very, very fast. And particularly if I send a very large message, MPI is going to do its best, the MPI software is going to do its best to maximize its capabilities and utilize all available bandwidth on the network. So you get as close to peak bandwidth as possible. Here's two examples just from products from my own company here. Let's say we have a scenario where we have two servers, a switch between them, and we're talking about user level processes on there. So let's say if you have DDR and InfiniBand and you start in one process on one server, you go out the network through the switch, through the network again, and back into the other server, you can get somewhere between 1 to 2 microseconds of half round trip 0-byte ping pong latency. And that's quite a mouthful there, but what that means is that that whole path that I traverse there You start in a user level process, go down to the operating system, go out through the network card, go out through the network, through the switch, through the network, back into the other network card, up through the operating system, and up to the other user level process takes a grand total of 1 to 2 microseconds. And you'll get a max peak bandwidth somewhere around 14 gigabits for large messages. And I'm giving round numbers here because it very much depends on the quality of your servers, the buses, your networking hardware, all these kinds of things. And so it's best, since we're talking at the high level here, just to give a range. Now for 10 gigabit Ethernet, you'll typically see somewhere on the order of 5 to 7 microseconds half round trip for 0-byte ping pongs. And you'll get much closer to the peak bandwidth. You'll get somewhere around 9.8, 9.9 gigabits per second for large messages. Now, MPI implementations of the standard, there are actually many of them. There are several well-known vendor ones, HP MPI, Intel MPI, Scali MPI, and many others. And they all have their own support channels. So you can call up these companies and say, hey, I'm having a problem with my application, or I'm not seeing the performance I believe I should be seeing. Normal support channel kinds of things. There are also open source MPI implementations out there, such as Open MPI and MPitch. And MPitch comes in 2 flavors, version 1 and version 2. They tend to rely on the open source community for support. So public mailing lists, Google searches, these kinds of things. But some also have vendor support as well. There's also a variety of research quality implementations out there. They're usually proof of concept and exploring some particular aspect of high-speed point-to-point communication or collective communication, or something about networking, something about parallel computing. They're not generally intended for production usage. They're just trying to use MPI as a vehicle for their research. So why are there so many MPIs out there? Well, it's a pretty complicated question. As you saw in the previous slide, some aim to make money. They're closed source, and they have support channels and all these kinds of mechanisms. Others target specific platforms. You might go to a specific kind of parallel computing platform, and there's only one MPI available, the one that was provided by the vendor. Others aim to be research, like I mentioned too. They're open source, and they're trying to explore some new ideas, and how do I move bytes from over here to over here, particularly in collectives or some other funky kind of new researchy way. But there's also a lot of history and politics involved, which is we're a relatively small community, and sometimes MPI implementations merge and unmerge, and there's been a rather complicated history of these kinds of things. Open MPI, the project that I work on, is kind of a fascinating blend, if I do say so myself, of both research and industry, and I'll talk a little bit about that in a few minutes. Now, the target audience for MPI is really, say, scientists and engineers. You don't really know or care how the network works. You're, say, a mechanical engineer, and your area of specialty is mechanical engineering and all the things surrounding that. A computer is just a tool to you, and you don't want to have to be a computer scientist to be able to compute something very, very large. So sometimes you're not even a very good programmer. And I don't say that in a derogatory way. Like, I mean, a computer is just a tool, and you want to be able to do your work using the computer with as minimal effort as possible. In that light, MPI is usually used for parallel computing, and I've cited that a few times in the slides already. So when you want to use tens, hundreds, or even thousands of servers, you want to have all of these machines working together as a single computational unit. And MPI is generally intended for what we call high-performance computing, and that's usually associated with parallel computing as well. So many servers working together, low latency, high bandwidth, all these kinds of metrics working together so you can get the maximum computational performance out of what you're trying to do. Now, parallel computing in itself, as I said, can use many processors. It's generally done when the computation is just too big for one server. Say you don't have enough RAM, or you don't have enough CPU power, or you don't even have enough disk, whatever your constraints are. So you spread the job across multiple servers, and you have all these processes working in all these servers working together in concert. Now, I'm particularly mentioning one kind of model here, but processors could be in one big box. There are quote-unquote big iron companies that will sell you, a machine that has lots and lots of processors in one box, or you could have a commodity cluster of a bunch of servers working together, whatever it may particularly be. So I'm particularly leaning towards the cluster-based solution simply because that's the type that I work on, but MPI encompasses all of these models. And as shown on the slide here, when you use all these processors together, you usually can aggregate the RAM and the processing power, and you can do things like divide and conquer the particular problem space that you're going to do. There's a lot of different models that you can do, but divide and conquer is an easy one to talk about. That every processor does a separate little chunk of the problem, and then you aggregate the results. Now, as I also mentioned before, MPI abstracts the network, so it doesn't really matter what the underlying network is. Is it sockets or shared memory, Ethernet, InfiniBand, or something else? It doesn't matter. Your application calls some relatively simplistic functions like MPI send and MPI receive, and the right stuff just happens underneath. So whether it's a socket or whether it's shared memory or something else, the right things happen and the bytes move from one process to another. Another major thing that you don't have to worry about is making connections. So with sockets, there's no need to worry about IP addresses or ports or any of that kind of stuff, or shared memory. What's the name of the memory map file, or should I use system? It doesn't matter. MPI takes care of that for you. And boy, even setting up InfiniBand queue pairs can be rather complicated. So let's hide all that kind of stuff from the target audience, the scientists and engineers and things like that, and just to have them do MPI send and receive, and the right stuff happens underneath. So if you recall our diagram from before, you can see that the user application and then the MPI middleware and the operating system here. So let's put this on a couple of servers here and see what it looks like. So let's say I have a 4-server cluster and I'm running one MPI process on every job, on every server. You can see there's 4 copies of the application, of the MPI stack and the operating system, and there's some kind of network joining them all together too. Well, here's kind of one of the nice things about MPI. I said this already about the abstraction of the network. Let's say I consolidate down to 2 servers. Now I'm running 2 MPI processes on each server, and so therefore, assumedly within each server, they're using shared memory to communicate, and then falling back to the network when they need to communicate off server. But to the application, they don't know. They're still calling MPI send and MPI receive, and the MPI implementation will automatically do the right thing to get the bytes to the right process, whether that uses shared memory or the back-end network. And then let's say we consolidate even further and we're down to 1 server with, let's say we've got 4 cores on the server. That's not uncommon these days, right? And assumedly inside here, they're all doing shared memory. But again, the API hasn't changed. You're just doing MPI send and MPI receive inside your application. Now, a little appreciated fact is that MPI systems, MPI implementations must also include some kind of runtime environment. They either include their own or leverage somebody else's, whatever, but consider that it's a fairly difficult task to start. Let's say you want to run a 10,000 process job. You got to start 10,000 processes. How do you do that? Well, the MPI generally has to do that. Now, depending on what your vendor is and what kind of machine you're running on, there's usually some kind of user level setup for the first time you do an MPI job. We typically see that this is a big source of errors, that people, first time users don't necessarily complete the first time setup or do it incorrectly and see a lot of issues there. So first time you run an MPI job, make sure your setup is correct and you're following all the documentation. Now, I just wanted to show a trivial MPI application here. This is really pseudocode too, because I snipped some things out for space. And I don't want to go through every line. I just want to give you an appreciation for the type of API that we're talking about here. The second line down, the MPI init, that's the first function call that you have to call an MPI before you can call any others. The next 2 down, MPI comRank and MPI comSize, tell you your identity and how many peers you have. MPI is actually strictly ordered such that when you have all these processes, you can say, oh, you are number 7 out of 9 total. And so it's a very common paradigm for many MPI applications to find out who they are and then use that to decide what part of the work and what part of the job they're going to do. And then further down, you see that we have these MPI send and receive calls here. And I'll explain the specific ordering here in a little bit, but you can generally see I'm just sending a message, and it's a typed message. I'm saying, oh, I'm sending 1 integer, and I just give it an integer value of a to and a from, who I expect to send it to and who I expect to receive it from. No IP addresses, no InfiniBand queue pairs, no shared memory map files, or any of that kind of jack. Remember, all that stuff happens magically underneath. And then finally, at the end of the day, you call MPI finalize, and that's kind of the opposite of MPI init. It's the last function that you call, and it shuts everything down. So what exactly does this application do? Well, this is what we call the canonical ring program. So the way it starts is we have, let's say we were running this program with 4 processes. The ball starts rolling, so to speak, with process 0. You can see in each of the boxes here I've calculated what the to and from values were from the C program there, or the C pseudocode that is. Process 0 starts the game off by sending to MPI 1. He does a send, and there's a matching corresponding MPI receive in process 1. So when 0 does a send and 1 does a receive, the bytes flow across the wire there, and 1 gets the message. He then turns around and does a send, and it's matched by a waiting receive in process 2, and so on, all the way around the ring there. And finally, actually, process 0 closes the ring again and does a trailing receive and gets the message. So it's just like the kindergarten game of telephone. You start going out the left, and it goes all the way around the message, and then it comes back in the right. Now, that's a bit about MPI. Let's talk a little bit about the Open MPI project. In some ways, it's yet another MPI implementation, but not entirely. It really replaces several prior MPI implementations. Open MPI actually represents the merger of several prior MPI implementations to create something better based on what we'd all learned over the past 10 years of MPI implementations. So it's kind of the idea of like, wow, why didn't we collaborate before? Because there's so many MPI smart people out there. We're really kind of silly not to try and collaborate and come up with something better. It's an open source project, and it's heavily influenced by both academic and research members and also industry members, and that's what the graphic on the right tries to represent there. It really represents a nice blend, and so we get cutting edge research also backed with industry standard QA tools and hardening to turn them into products that customers can actually run. So it's a wonderful project, and we try to get the benefits of both sides. Now, a little bit on Jeff's type A personality here. One thing just to educate you on, Open MPI is actually 2 words. I see it all over the web and all over the net, and email messages and things like that where people smush it together, Open MPI in 1 word. It's not. It's actually 2 words. You'll frequently hear me say OMPI too, O-MPI, Open MPI, and we just pronounce that OMPI, just an abbreviation for Open MPI. So Open MPI is fundamentally based on plugins, and you might hear me say the word component or module, and those have slightly different meanings, but generally we're just talking about plugins. Everybody understands plugins. Open MPI has plugins for everything. We have plugins for the back-end resource manager. Are you running Slurm? Are you running Torque? Are you running LSF? Are you running SGE? Whatever. Open MPI has a plugin for that. What's your back-end network? Is it TCP? Is it InfiniBand? Is it shared memory? Is it something else? We have plugins for all these different kinds of networks. What's your back-end checkpointer? Is it BLCR? And so on and so on and so on. There's somewhere around 30 different types of plugins for Open MPI right now, and that number goes up or down per release when developers add and remove types of plugins based on things that are going on in the code base at the time. But really, the general theme that we're trying to get across here with the plugins is that you can make runtime decisions about how you want Open MPI to behave. You don't have to recompile and reinstall either your application or Open MPI. You can just pass in a flexible set of parameters to Open MPI and say, I want you to do this in this run. And then when that run's done, you can run another one with a different set of parameters. For example, first run your job over InfiniBand, then second run your job over TCP Ethernet and see how it goes. So here's a plug-in high-level view of Open MPI. This diagram is very similar to one that we saw earlier in the slides. Again, top-level user application. Next level down is the MPI API. And then everything in blue there is the Open MPI implementation. I didn't really show the operating system underneath here. But MCA, the modular component architecture, is kind of the backbone of Open MPI. It's our plug-in system. It's our runtime parameter system. It's everything. Underneath the MCA, we have a series of frameworks, and a framework is really a type of plugin. So, Resource Manager is one framework. Point-to-point network is another framework. Collective algorithms for MPI, collective operations is another one, and so on and so on. This is the type, there's approximately 30 of these or so. And then under each framework, we have, an instance of the implementations for these things. So we have a component or a plugin for Slurm, and a component or plugin for Torque and SGE, and so on and so forth. So this is an architectural view of how Open MPI works. I do want to stress this is not a layering diagram. So when you call MPI send, we don't have to go through all these layers to get to the backend network. This is just how the code is laid out and how it's architected. Now, I've given you quite a bit of information here, but here's a few places to get a little more. The official MPI Forum website is www.mpi-forum.org. You can find the MPI 1 and 2 specs there, and eventually the 2.1 and 2.2 and 3.0 specs will be there as well. The Open MPI website is listed there as well. It's open-mpi.org. And we have a very extensive FAQ on there, so feel free to browse through that. Also, several years ago, I wrote a column for a magazine about MPI, and that magazine is unfortunately now defunct, but the text of all my columns are there. It's also a good 50,000-foot view of MPI and dives in to, say, the 20 or 10,000-foot view on various topics. Could be useful reading if you're just starting to learn about MPI.